Inside this syringe is the most reactive metal on Earth, cesium. And when it comes into contact with air, this happens. It catches fire. Even though cesium is incredibly reactive, making the metal itself is actually not the hardest part. What is much harder is purifying it afterwards so it's completely free of impurities and shows its beautiful color in all its glory. About 3 months ago, I received an email from a professor at a university in Belgrade asking whether I could do exactly that. Make a clean ampoule of cesium that would later be displayed in a large periodic table at the university. And because it had already been several years since I last made a truly clean ampoule of cesium, and because I really liked the idea of it being displayed in a huge periodic table, I agreed. I mean, I had already made a clean ampoule before, so doing it a second time should be relatively easy, right? It wasn't. Not even close. This quickly turned into one of the most irritating projects I have ever taken on. But why is it so difficult to make a pure ampoule of cesium? The problem is that cesium is so incredibly reactive that even tiny traces of oxygen or moisture are enough to oxidize it. And once that happens, it starts sticking to the glass. That means the metal has to be distilled twice under vacuum in an apparatus made entirely from glass, and then the ampoule has to be sealed off under vacuum as well. And a glass apparatus like that is not something you can just buy. So everything starts with me building it myself from a few glass tubes and round bottom flasks. I'm using an oxygen propane torch, which honestly is a bit too small for what I'm trying to do. But you have to work with what you have available. With the torch I can melt the glass and join the parts together. Through a hose I blow air into the glass to prevent it from collapsing inward. Apart from the fact that I'm not a professional glass blower, it had also been quite a while since I last made a distillation setup like this myself. So I was definitely a bit out of practice. But in the end, it doesn't have to look pretty, it just has to work. The only part that will remain from the whole setup at the end is the ampoule itself. In theory, cesium could also be distilled in a ground glass apparatus like the ones you usually see in chemistry labs. And in fact, that is exactly what I did in one of my first cesium videos. The problem, however, is that even well-greased ground joints are never 100% airtight, and the grease itself can also introduce impurities into the cesium at the temperatures needed. That is why, if you want a truly clean ampoule, you need an apparatus made from a single, continuous piece of glass. The actual ampoule that I will be distilling the cesium into was not made by me, but by a friend who is a glass blower. Because this ampoule is going to be displayed, it should look as beautiful as possible. And in that respect, the work of an actual glass blower is on a completely different level than mine. So a huge thank you to Johann for not only making this ampoule, but many more for me. Why do I need more than one ampoule, you ask? Well, as I said, this project really tested my patience. But we will get to that. Once I had finished making the still, I cleaned it several times with hydrochloric acid, then with distilled water, and finally with isopropanol and dried it under vacuum. And this is what the finished still looks like. Maybe I should explain what this strange shape is all about. And yes, the still you are seeing right now is a different one from the one I just made. Spoiler alert, I had to do this distillation more than once. But back to how it works. I will fill the cesium into the first flask and melt off the side arm afterwards. That way the whole apparatus is hermetically sealed. Then I heat the cesium inside the first flask and distill it into the second one. Once that flask is full, I melt off the first part of the still and then distill the cesium a second time directly into the ampoule, which is then also sealed off under vacuum. If I were to use the still in its current state though, that would actually be pretty dangerous. Why? Because when the glass is melted and then cooled down relatively quickly afterwards, stress builds up inside the glass. That can cause it to crack when reheated, or in some cases even on its own. Using a so-called polariscope, I can make these stresses visible to the naked eye. It's actually pretty easy to build yourself. I use an LCD monitor as a source of polarized light and hold a polarizing filter in front of the camera so that the light is blocked. If I now hold the still between the filter and the monitor, you can see that all the areas that were worked with a flame glow blue. That happens because the glass changes the polarization of the light in those areas, which allows it to pass through the second polarizing filter. And even though this blue glow looks nice, it is dangerous for exactly the reasons I just mentioned. To remove the stress, the still is heated in a furnace to about 560 degrees Celsius and then cooled down slowly and evenly, which allows the stresses to relax. And if you look at the still again under polarized light afterwards, you can see that the glow has disappeared. So the glass no longer contains any significant internal stress. That means I can now move on to the most dangerous step of the entire project, distilling the cesium inside this apparatus. Since the boiling point of cesium at normal pressure is around 670 degrees Celsius, I will distill it under vacuum. For this, I connect the still to a rotary vane vacuum pump. On the vacuum line, there are two valves that allow me to either apply a vacuum to the still or fill it with argon. Using a Pirani sensor, I can measure the pressure inside the system. The multimeter shows me a voltage, which I then have to convert into a pressure reading. Unfortunately, I currently don't have the money to buy a dedicated readout unit for the sensor. Some of you are probably wondering how exactly I plan to connect this all-glass still to the vacuum pump. For that, I use this adapter that I designed and had manufactured. On one side, it has a KF flange that connects to the vacuum hose. On the other side, it has a female NS14 ground joint that I can connect to the joint attached to the still. To make this connection vacuum tight, I use a special high vacuum grease that I apply to the ground joint. This grease fills all the tiny imperfections and thus creates a better seal. I know, I said earlier that cesium distilled in a setup with ground joints can never be absolutely pure. But this connection never comes into contact with the cesium, and I'm also using a special high vacuum grease, so in this case it's acceptable. And besides, you always need some kind of transition from the glass apparatus to the vacuum pump. Once everything was assembled, I closed the side arm of the flask with a stopper and applied a vacuum to the still. Then I heated the still with a torch until the yellow sodium flame became visible. This is done to remove moisture adsorbed to the glass surface. Even if surfaces look dry, there are always traces of moisture on them, and that moisture would react with the cesium and contaminate it. Once the whole still is hot, I fill it with argon and immediately pull a vacuum again. That way I can sweep the water that was removed from the surfaces out of the still. After repeating this process, which is also called flame drying and purging 3 times, I can move on to the next step, transferring the cesium into the still. If you are wondering how I got this much cesium in the first place, you should probably watch one of my videos on making the metal. I linked them in the video description. Right now, the beautiful golden metal is still inside this flask. It already looks relatively clean, but it's still nowhere near the purity it will have once I'm done. But let's not forget, this metal is so reactive that it can catch fire on contact with air. That means I need to use a special technique to transfer it into the still without exposing it to the atmosphere. To do that, I first connect a hose which is connected to the argon cylinder to the flask. Then I use a hot air gun to melt the cesium inside the flask. Since the metal already melts at about 29 degrees Celsius, it really doesn't take much to liquefy it. As soon as it's molten, I remove the stopper from the flask. Because argon is flowing through the flask the entire time, the cesium is protected from air and moisture. Then I place a so-called septum on the flask instead of the stopper. A septum is a rubber cap that allows me to push a thin copper tube through it. I then guide the other end of the copper tube through the sidearm into the still. While the sidearm of the still is open, argon is also flowing out of the still to prevent moisture and oxygen from entering the previously dried glass apparatus. Now, if I push one end of the copper tube below the surface of the molten metal, the argon overpressure forces the cesium through the tube into the still. The argon flowing through the still protects the cesium that is now inside of it. Once the flask of the still is full, I pull the copper tube back out of the cesium in the original flask so that the argon pushes the last remaining drops from the tube into the still. Then I remove the copper tube from the still and seal it with a stopper. After that, I need to melt off the neck through which I filled the cesium into the still. This hermetically seals the entire apparatus, leaving only one remaining opening connected to the vacuum pump. While melting off the sidearm, I open a three-way valve in front of the still. That prevents overpressure from building up inside, because otherwise the soft glass would inflate like a balloon and it would be almost impossible to seal the neck properly. Normally, you would use a handheld torch for this. But since I don't have one, I use the same bench torch I used to build the still. It's a bit awkward, but it works. After sealing the neck, I use a regular torch to let the glass cool down more slowly. I do that to reduce stress in the glass, which could otherwise cause cracks. Because in case you don't remember, stress in glass is dangerous and can lead to cracking. This method, called flame annealing, is of course nowhere near as good as properly annealing the still in a furnace, but at this point that is no longer an option. Once the still is sealed, I pull a vacuum again and heat the apparatus under vacuum 3 more times, flushing it with argon in between. Then I begin heating the flask with a torch until the metal starts to evaporate. At first you can see a golden shimmer appear in the glass tube, and over time this turns into larger droplets of cesium. The way the cesium condenses on the glass wall and then runs back down really is beautiful. And there are probably not many people in the world who have ever seen a metal being distilled. The cesium rises through the glass tube above the flask, condenses, and then drips into the second flask. You can already see that the surface of the metal looks much better immediately after the first distillation. You can even see the vibrations of the vacuum pump in the surface of the golden liquid metal. While the distillation is running, let's quickly answer a question I get all the time in the comments. Isn't cesium radioactive? Well, let's find out. If I hold my radiation detector from Radiacode, the sponsor of today's video, next to this ampoule of cesium, we see absolutely nothing. Even though the scintillation detectors from Radiacode are significantly more sensitive than a typical Geiger counter, the reading doesn't change at all. And the reason is quite simple. The naturally occurring isotope of cesium isn't radioactive. Only certain artificial isotopes like cesium-137 are radioactive. These were produced during nuclear weapons tests or released in nuclear accidents. Because of that, small traces of cesium-137 can still be detected in the environment today. If I take ash from burnt mushrooms and record a gamma spectrum with the Radiacode detector, you can actually see the characteristic gamma peak of Cesium-137. And that's just one of many features available in Radiacode's mobile app. So even though many people associate cesium with radioactivity, mostly because of nuclear accidents, the naturally occurring isotope itself is not radioactive. A big thank you to Radiacode for sponsoring this video. If you're interested in a compact, accurate and highly sensitive radiation detector yourself, you will find a link and a 5% discount code in the video description. And now, back to the distillation. During the distillation, I measured the temperature of the flask with an infrared thermometer, and it was about 250 degrees Celsius. I'm not going to distill all of the cesium into the second flask though. I will leave a small amount behind in the first flask. That way I can prevent higher boiling impurities from being carried over into the second flask. But already during this distillation I noticed the first serious problem. Do you see this white to slightly grayish coating on the glass where the clamp is holding the still? At least as far as I remember, that is not normal. It suggests that the metal is slowly oxidizing. Why that was happening, I honestly could not explain at the time. But I had no choice. I had to keep going. Because once the distillation is running, there is basically no turning back. So that meant it was time for the next critical step. I had to melt off the first part of the still, under vacuum. Because even though argon 4.6, the grade of argon I'm using, contains only 0.004% of impurities, and only part of that is oxygen and moisture, that is still enough to contaminate the surface of the cesium. Even if I had a theoretical argon with 100% purity, it would still pick up moisture from the plastic tubing connecting the argon cylinder to the apparatus. There are theoretical solutions to this, like using connections made entirely of metal that can be heated under vacuum to remove adsorbed water. But that would make the setup much more complicated and, above all, much more expensive. So I chose a different route. Once the distillation had started, I would never again let argon into the still and instead perform all remaining steps entirely under vacuum. To make melting off the first section easier, I had built this constriction into the still when I made it. To reduce the risk of the glass cracking from heating it too quickly, I first warm it with a regular torch. Then I use my oxygen propane torch again to heat the glass until it collapses. Then I can slowly pull it apart and permanently seal that section. Here too, I use a regular torch afterwards so the glass cools down more slowly. Once I had sealed off the first section, I reheated the empty part of the still as well as the ampoule itself with a torch to make absolutely sure there was no moisture left on the glass surface. Now I could distill the cesium from the second flask into the ampoule. And during this distillation step, I noticed even more problems. The cesium in the second flask had visible impurities floating on its surface. The camera could not really capture them, but they were there. Since the glass surfaces had been heated extremely thoroughly, the reason for the contamination could really only be the vacuum pump or the connection between the still and the pump. Maybe the connection using my adapter was not actually 100% leak tight after all. And while the cesium flowing into the ampoule was, for the most part, beautiful, there were also signs of contamination here. In some places, the metal was sticking to the glass, which normally suggests that it's not absolutely pure. Much later, however, I would find out that the reason for this was actually something else. Once the ampoule was about half full, I sealed it off. As I have explained earlier, this also has to be done under vacuum. Before we look at the finished ampoule, let's briefly talk about what I do with the cesium that I leave behind in the still. Because disposing of that much cesium safely would be really annoying. So I first filled the still with argon and then scored the glass above the flask with a glass cutter. Then I placed a drop of hot glass on that spot so the glass would crack. At that moment, oxygen and moisture obviously enters the flask, but if I'm fast enough, most of the metal is still protected by the argon inside. I then clamped the separated flask in a stand and let argon flow in it from above through a glass tube to protect the metal. Then I melt the cesium with a hot air gun and use a syringe to transfer it back from that flask into the one it originally came from. That way I can recover most of the cesium. The small amount of cesium left behind in the flask can then be reacted relatively easily with isopropanol while argon is still flowing through the flask. So, let's have a look at the ampoule. At the moment, the entire upper part is still covered with tiny cesium droplets because when the ampoule was sealed, some cesium evaporated and condensed on the cold inner wall of the ampoule. If I melt the cesium and let it flow over that area, this thin film disappears again. And even though this ampoule is cleaner than any other ampoule ever made by a YouTuber, and probably even cleaner than some ampoules you can buy, I was not happy with the result. On the one hand, you can see impurities floating on the surface. And on the other hand, there are areas where the cesium clearly sticks to the glass. Especially in the lower part of the ampoule, the cesium deposits in a ring-like pattern. Normally, that is a sign of contamination. As you can see in my video from about 3 years ago, truly clean cesium behaves almost like water on a hydrophobic surface and beats up instead of wetting the glass. So, the final result was, to put it mildly, deeply disappointing. The still is a one-time use item, and for a second attempt I would have to make a completely new one, anneal it, and then spend another full day from 8 in the morning until 10 at night distilling the cesium all over again. But at that point, I had no idea that the frustration was only just beginning. When I made the still for the cesium, I had also made a second one with smaller 50 ml flasks. It was originally intended for the distillation of rubidium, but I decided to use this smaller still for a second attempt. At that point, my biggest suspicion was that the ground joint to KF adapter was not completely vacuum tight. Because at the start of the distillation, the cesium in the second flask still looked very good. Only later did impurities appear on the surface. That could be explained by oxygen leaking into the still through the ground joint during the actual distillation. So I decided to remove the joint and replace it with a simple, thick-walled 10 mm glass tube. After attaching that tube, I of course had to thoroughly clean the still again and anneal it in a furnace. To this glass tube, I could then attach a special vacuum adapter that seals using 2 O-rings pressed into the outside of the tube. This type of connection is also used in high vacuum systems and is definitely the better choice compared to a greased ground joint. So this way, I could be absolutely certain that this connection was no longer the problem. But just to make sure I would not end up wondering later whether there still might be a leak somewhere, I used another special method that is normally used to find leaks in high vacuum systems. a helium leak detector. This is a special instrument that I can connect to the still, and it has its own vacuum pump that evacuates the system. Inside this instrument, there is also a mass spectrometer specifically designed to detect helium atoms. In simple terms, it is an incredibly sensitive helium detector. Once the setup is connected and under vacuum, I can spray helium gas onto every connection point. If there's even the tiniest opening, helium will enter the apparatus and be detected by the leak detector. But there was absolutely no signal, which meant the apparatus was tight. So far, so good. Which of course meant it was immediately time for the next problem. The small flask I had taken the cesium from for the first distillation was almost empty, and there was simply not enough left for another distillation. That meant I had to open one of the large ampoules and use some of the cesium from there. At least that gave me the opportunity to show you how I get the cesium back out of a sealed ampoule, because that was a question I got all of the time under my original video. The ideal way would obviously be to bring the ampoule into a glove box filled entirely with argon or nitrogen and open it there. But I do not have a glove box, so I have to use a slightly less ideal method. The process for opening the ampoule is basically the same as the one I used to remove the flask from the still. First, I score the neck of the ampoule with a glass cutter. That creates a predetermined breaking point. Then I touch that spot with a glass rod carrying a drop of hot glass, and the ampoule breaks cleanly at that line, and I can then remove the upper part of the neck. Because the ampoule is filled with argon and argon is heavier than air, the metal is temporarily protected from oxygen and moisture even after opening it. Still, I immediately place a septum on top with a needle already inserted through it so argon can flow in. This method is not ideal, and some oxygen and moisture will always get into the ampoule, but for this purpose, it's good enough. After that, I proceed exactly the same way as when I transfer cesium from a flask. I push a copper tube through the septum of the ampoule, with the other end reaching into the still. Then I melt the cesium inside the ampoule using a hot air gun, and the argon overpressure pushes the metal into the flask of the still. Once I have transferred enough metal, I reseal the ampoule. To do that, I pull out the copper tube and open a valve in front of the ampoule so that there is argon inside the ampoule but no overpressure builds up. Then I can melt off the neck using my oxygen propane torch. That way, the ampoule is hermetically sealed again and can be stored safely. And now that this problem is solved, we can immediately talk about the next one. When I pulled out the copper tube, I accidentally smeared some cesium onto the inner wall of the sidearm that I was about to melt off. And that is bad, because under these conditions, the cesium will not evaporate cleanly without leaving residue, because it has already partially oxidized. And those residues can weaken the sealed off section. You can see that when I melt off the glass, it glows red. And if you know what clean glass normally looks like during sealing, the difference is obvious. Even after sealing it off, you can see that the area looks cloudier than usual. Now, the risk that this spot would actually break is relatively low, but it still made me nervous. Because after seeing what happens when just a few drops of cesium come into contact with air, you can probably imagine what would happen if the still were to fail while containing boiling cesium at 250 degrees Celsius. Nevertheless, I started distilling the cesium from the first into the second flask. And at the beginning of the distillation, everything looked perfect. The metal behaved exactly the way I was used to. It really beaded off the glass surface of the flask and looked flawless. But after a while, my optimism disappeared. When the second flask was almost filled with the amount of cesium I needed, the surface again started to look slightly different. And on top of that, this time there was a grayish to silvery impurity visible in the first section of the still. That was something I had never seen before during the distillation of cesium. Interestingly, this impurity also did not react immediately with water after I opened the still. While I was distilling the cesium from the second flask into the ampoule, I kept looking for an explanation. The cesium in the second flask only started to look different near the end of the first distillation, and there was also that silvery impurity in the first section of the still. That made me think, maybe the cesium contained impurities with a slightly higher boiling point that only came over at the end of the distillation and contaminated the metal. The second possible explanation was still the vacuum pump. Maybe tiny amounts of oxygen were flowing back from the pump into the still and oxidized the cesium surface over the course of the distillation. And as I watched the metal flowing to the ampoule, I became more and more convinced that the cause either had to be an impurity in the cesium itself or an issue with the vacuum pump. After I sealed off the ampoule, it was obvious that it looked much better than the first one, but it still was not perfect. Here too, in a few places, you could see that the cesium was sticking to the glass. I honestly couldn't end the project like that. I knew I was capable of making a better ampoule. So that meant I would try it one last time, and this time eliminate both possible causes as well as I possibly could. Which also meant I had to build a third still. While the new still was being annealed in the furnace, I could at least already address the issue of possible higher boiling impurities. For that, I would first distill the cesium in a ground glass apparatus and try to control the temperature as precisely as possible. Normally, I only have a few pieces of glassware with ground joints. So I would like to take this opportunity to sincerely thank the HWI Group, a company specializing in innovative technologies and pharmaceutical services for the pharma and biotechnology sector. Some time ago, the HWI Group generously donated a large amount of glassware and laboratory equipment to me, which I am now able to use. And yes, I know that at the beginning of the video, I said that you cannot get a perfect ampoule using a ground glass apparatus. But that is not the goal of this step. This is just a first purification before the cesium is later double distilled again in the all glass apparatus. For that, I first had to transfer cesium from a large 2-liter flask into a 250 ml Schlenk flask. If you watched my last video and were wondering where the 400 grams of cesium missing from the large flask at the end of the video had gone, well, now you have your answer. After transferring the cesium into the flask, I attached a distillation bridge. And of course, I had also flame dried it and the receiving flask and flushed them with argon to remove any moisture and oxygen. Then I applied a vacuum and heated the flask with a torch. My plan was to distill only a small amount of cesium and discard that first fraction. That way I hoped to separate any lower boiling impurities. So, after distilling about 5 milliliters of the metal into the receiving flask, I stopped the distillation and filled the apparatus with argon. And here you can see very nicely what I was talking about earlier. Even though I am introducing argon into the distillation setup, you can see how the surface of the cesium visibly tarnishes, because the argon carries moisture and oxygen from the tubing into the system. I then replaced the receiving flask and applied a vacuum again. This time, however, I did not heat the large flask with a torch, because I wanted to avoid overheating the metal. Instead, I used a heating mantle whose temperature I could monitor precisely with a thermocouple. This way, I could keep the flask just above the boiling point of cesium and hopefully leave all less volatile impurities behind in the flask. After a while, the flask reached a temperature of about 280 degrees Celsius and the head temperature was 170 degrees Celsius. The head temperature normally reflects the temperature of the vapor just before it condenses in the condenser. Usually, you would measure that inside the apparatus right before the condenser. In my case, I simply attached a temperature probe to the outside of the glass. That is not quite as accurate, but it still gives a good idea of whether the temperature is changing. And I will never get tired of how beautiful liquid cesium looks flowing down a glass surface. At the same time though, that sight is also a little annoying. Because why does the metal beat up so nicely on this glass surface here, while in the ampoule, which was dried much more thoroughly, it does not? Honestly, it's a bit of a mystery to me. Maybe the exact composition of the glass and therefore the manufacturer also plays a role? Once the 100 ml flask was about half full, I stopped the distillation. On the one hand, that was all I needed. And on the other hand, I wanted to leave as much metal as possible behind in the first flask, along with any impurities it might contain. So I filled the apparatus with argon, removed the small receiving flask and sealed it. Then, while argon was flowing through both the flask and the condenser, I tilted the apparatus slightly so that the remaining cesium in the condenser could flow back into the flask. Every drop of metal that I can get back into the flask now is one less drop I will later have to quench and neutralize. Then I removed the condenser and placed it in a steel bucket. In general, all equipment that has come into contact with cesium is stored in a steel bucket before I neutralize the remaining metal. In the same way, all paper towels I used are collected in a large beaker, soaked with water, and then left to sit for a day to make absolutely sure that no cesium remains on the towels that could later ignite. Normally, I let argon flow through the glassware while I slowly add isopropanol to react with the cesium. If you do not use argon, it's almost guaranteed that the alcohol will catch fire. And you can see that very clearly here. In that case, the best thing to do is either let the alcohol burn off in a controlled way or smother the flames with a lid. As a final step, I add water to all the equipment to make absolutely sure that no cesium remains. Now that I had, so to speak, pre-purified cesium and removed the possible impurity, let's talk about my second suspicion. That maybe oxygen or moisture from my vacuum pump was flowing back into the still. To completely rule that out, I decided to use a turbomolecular pump. This is a special type of vacuum pump used to reach the high vacuum or even ultra high vacuum range. These are pressures you would never reach with a normal rotary vane pump. Inside this pump is a rotor that looks very similar to the rotor in a turbine. This rotor spins at about 60,000 revolutions per minute and transfers the impulse from the rotor blades to the individual gas molecules. By placing this pump between my rotary vane pump and the still, I can ensure that no oxygen or moisture from the roughing pump can flow back into the still. A cold trap with liquid nitrogen would have had a similar effect, but I also wanted the added benefit of the lower pressure. By the way, here you can see a much larger turbomolecular pump. But for the distillation, the smaller version is much more practical. Since these pumps are sensitive to vibrations and movement, I designed and 3D printed a special mount that allows the pump to be securely fixed to the table. Strictly speaking, high vacuum is not really that important for Schlenk technique, meaning working under inert atmosphere. Because with repeated evacuation and backfilling, in other words, purging with argon or another inert gas, you are basically replacing all gas molecules in the apparatus with inert gas anyway. Even if the apparatus still contains, say, 0.1 millibar of pressure, that residual gas will be unreactive. So for Schlenk technique, repeated purging with argon is much more important than the final pressure. And even in terms of high vacuum, the whole thing makes relatively little sense, because the opening of the still is very small. That means that at these low pressures, in the regime of molecular flow, it takes a very long time for the gas particles to travel from the still to the pump. But that's not the point. I'm not trying to reach the lowest possible pressure. I just want to prevent anything from the rotary vane pump from backstreaming into the still. And this is what the finished setup looks like. The argon inlet is installed through a needle valve upstream of the turbomolecular pump. That way, the gas does not have to pass through the pump itself, which could potentially introduce contaminants. To measure the much lower pressures, I'm now using an ionization vacuum gauge. What hasn't changed, however, is that I still read the pressure like a peasant using a voltage and convert it afterwards. Once everything was assembled, I baked out the still 3 times under vacuum, flushing it with argon in between. And I have to say, compared to my first attempt, this still looks significantly better. Apparently, I was slowly getting back into practice. You can also see that I made the tube above the first flask longer. The idea was for it to act as a column, improving the separation of impurities. Then it was finally time to transfer the pre-distilled cesium into the apparatus. If you compare it to the undistilled cesium on the right, you can see that the color is noticeably lighter. Maybe that's where the myth comes from that absolutely pure cesium is silver. I've actually read that comment several times, but it's simply not true. After transferring the cesium into the still, I sealed the sidearm once again and baked out the system 3 more times. This time I also heated the stainless steel hose that connects the still to the vacuum pump. After that, I started the turbomolecular pump and waited until the pressure dropped to about 10 to the power of -5 millibar. Then I heated the still, the ampoule and the hose once again. For this distillation, I had initially planned to heat the flask with a heating mantle. At around 200 degrees Celsius, the first traces of cesium started condensing as a thin film in the upper part of the still. To speed things up a bit, I insulated the glass with aluminum foil. But even then, it took an extremely long time before the metal vapor reached the constriction leading to the second flask. You can see, however, that some of the cesium travels much farther through the apparatus than in the previous attempts. That's because the pressure is lower, which means the mean-free path is longer. In other words, the cesium atoms can travel farther before colliding with another particle or the wall. After about an hour, it became clear that the heating mantle simply wasn't going to work. At least not in a reasonable amount of time. There was just too much glass between the first and the second flask for the metal vapor to heat it to the boiling point. So I removed the insulation and the heating mantle and, just as before, heated the flask with a torch. This was now the 3rd time I distilled the cesium from the first flask into the second. And I have to say, very few things look as fascinating as the distillation of a metal. The droplets condense on the glass wall and almost seem to move toward the next flask by themselves. My guess is that they are being dragged along by the cesium vapor. But if you have another explanation, let me know in the comments. There's also something else I want to address briefly. Some of you will probably say that the places where the cesium sticks to the glass in the ampoule are simply caused by contamination on the glass itself. And while the ring-shaped deposits do look a bit like that, I think it's very unlikely. For one thing, I cleaned the glass extremely thoroughly, so any contamination should have been removed. And secondly, the high temperature during annealing should have burned any organic residues. When you inspect the glass against the light, there is no visible trace of contamination. Watching the distillation proceed, I really started to think that the turbomolecular pump had made a crucial difference. This time, the cesium collecting in the second flask looked absolutely perfect. Even near the end of the first distillation step, the surface remained completely flawless, and that gave me serious hope. Okay, the first part of the distillation is done. It took way longer than I thought it would. This whole project takes way longer than I thought it would. But the cesium in the second flask looks perfect. So I really hope this attempt will be successful. But it also means that if anything goes wrong, sealing off the first part of the still, besides the danger, this whole progress would be lost. So let's go. Fortunately, sealing it off went smoothly without any major problems. Only the plastic part of a clamp suffered a bit. Oh, and if you've made it this far into the video, consider leaving a like and subscribing to the channel. If you would like to support me even further, you can become a channel member or a Patreon supporter. You will find a link in the video description. After sealing off the first section of the still, I heated the ampoule once more. At this point, the repeated flame drying might seem a bit paranoid, but I didn't want to risk any volatile impurity on the glass surface, causing the cesium to stick again. Then I began distilling the metal from the second flask into the ampoule. I'm already seeing these rings again where the cesium sticks to the glass. And I have no idea why. The cesium looks perfect in the second flask, it looks perfect in the ampoule. Maybe it's some impurity on the surface of the glass, but interestingly, if I heat those spots, the cesium evaporates again without leaving any residue behind. To me, that strongly suggests that the cesium had not chemically reacted with anything on the surface. If it had, it wouldn't simply disappear without leaving a trace. So I became increasingly convinced that what I was seeing was purely mechanical adhesion caused by the surface structure of the glass. In any case, I had no choice but to finish the distillation and seal the ampoule. And yes, overall, the result looked beautiful, but it still wasn't perfect. And at this point, that was slowly driving me insane. So, as you have seen, there's still this area, this circle, where the cesium sticks to the glass. I'm absolutely certain it's not an impurity in the cesium itself. The cesium looked absolutely perfect. I'm sure it's an impurity or a property of the glass itself, because these rings are basically the area right next to the spot you heat and you melt when you make these ampoules. I've noticed something similar when working with quartz glass. You get this frosted ring right next to the place you heat with the flame. Maybe it's something similar. I think it's an understatement to say I'm disappointed. Also disappointed in myself. I should have cleaned these ampoules with everything I had available. Piranha solution and probably aqua regia. I just assumed, I've cleaned them with acetone, isopropyl alcohol and distilled water. And then they were heated in an oven at 550 degrees Celsius for several hours. Not several hours at 550 degrees Celsius, but the whole process of heating it up and cooling down takes several hours. So there's no way it's something organic. And I also heated them under vacuum. So it has to be something inorganic, or maybe not even impurity. Maybe you can't remove this. I didn't have this problem with the first cesium ampoule I made several years ago, but I don't think I will do this again. It's now 11 p.m. I started here at 8 a.m. and as you know, this is the third time I am distilling the cesium. So yeah, I won't do this again. I think at some point you just have to accept that not every story has a perfect ending. Yeah.
There is a hook in me, one that you cannot see, but it is there. And you think I have a choice? There is no fucking choice.
I just couldn't accept that the ampules still weren't perfect, especially since I didn't understand why. So I built a fourth still. This time I decided to clean the ampule so thoroughly that I could be absolutely certain no impurities remained. Assuming that had even been the problem in the first place, which I honestly doubted. First, I prepared a solution of potassium hydroxide in isopropanol and filled the ampule with it. This solution is commonly used in laboratories to remove stubborn contamination from glassware and should dissolve any organic residue. However, potassium hydroxide slowly attacks glass, so I only left the solution inside for about 30 minutes before removing it and rinsing the ampule with isopropanol and distilled water. Next, I filled the ampule with a mixture of 3 parts concentrated hydrochloric acid and 1 part nitric acid. Together, these form aqua regia. This extremely oxidizing mixture should destroy virtually any organic or inorganic contamination. Just to be absolutely certain, I even heated the aqua regia until it was boiling. Then I emptied the ampule, refilled it with fresh aqua regia and boiled it again. And something interesting happened. Tiny bubbles appeared exactly in the areas where the cesium usually sticks to the glass. To me, that suggests the presence of nucleation sites. Since those spots did not disappear after the acid treatment, they clearly weren't caused by contamination. My conclusion was that the glass in those regions was simply rougher than elsewhere, which fits perfectly with the idea that the problem is related to the surface texture of the glass. After the second cleaning step, I rinsed it several times with distilled water. During the final 2 rinses, I even heated the water to boiling inside the ampule before pouring it out. Then the entire still was dried under vacuum once again before starting the next distillation. I won't make you watch the entire 4th attempt. The procedure was essentially identical to the previous runs. The still was thoroughly flame dried and flushed with argon before the cesium was transferred into it. This time, however, I also aimed a hot air gun set to about 650 degrees Celsius at the ampule throughout the first distillation step. And then I distilled the metal from the second flask into the ampule. And, well, it still didn't work. At first glance, the 4th ampule I made looks great, but again, there are these areas where the cesium sticks to the glass. At this point, I'm convinced that it's not an impurity on the surface of the glass, it is a property of the glass itself. Maybe microfractures or some surface unevenness forms when these ampules are made, and the cesium basically sticks to those areas or flows into the micro cracks. That's the only explanation I have. Because if you heat those areas, the cesium evaporates without leaving any trace behind. So it has to do something with surface texture, I believe. If you're an expert in glass and have any idea, let me know. I mean, the ampules I made still look great if you display them in a periodic table, but still a little bit annoying. That's life, I guess. But yeah, this time will have been the last. I won't do this again. I really hope you enjoyed today's video. Thank you a lot. Yes, I know, but I just couldn't stop there. I repeated the distillation again using borosilicate glass from a different manufacturer and also annealed it at a slightly higher temperature for a longer time. But even that didn't change anything. The cesium still stuck to the same regions of the ampoule. Eventually, I had one final idea. And the sixth and truly last distillation would show whether this would solve the problem once and for all. My suspicion was that flame drying the ampoule with a torch was causing new stress to build up in the glass and was changing the surface in some way, which then caused the cesium to stick to the wall. Because if you look at parts of the still that were heated less intensely, the cesium beats off perfectly there. So, for the very last time, I built another still. 6 times the charm, right? This time I made the ampoule myself. It definitely doesn't look as nice as one made by a professional glassblower, but it was good enough to test the idea. So, I repeated the entire process again. This time, the cesium came from ampoules that had been produced using a different batch of lithium, and it no longer produced those strange silvery deposits in the still. Looking back, I think my whole theory about higher or lower boiling impurities was probably a dead end. While distilling the metal into the second flask, I gently heated the ampoule to about 250 degrees Celsius using a hot air gun. That was enough to remove moisture from the surface while avoiding any additional thermal stress. And after sealing off the first section of the still, I began distilling the metal into the ampoule. At this point, I was convinced the problem had finally been solved, which made what I saw next even more frustrating. After just the first few drops entered the ampoule, the cesium once again stuck to the glass in exactly the same ring-shaped region. Above and below that area, the metal beats off perfectly. So at this point it was clear that the problem was not an impurity in the metal itself. I talked about this issue with the professor who had originally requested the ampoule. His suggestion was that sodium oxide might have evaporated from the molten glass during production and condensed in those regions, triggering a process called devitrification. In this process, the glass locally transitions from an amorphous structure into a crystalline one. That's definitely a plausible explanation. However, I would normally expect some visible cloudiness if the glass had started to crystallize, and I couldn't see any. So if any of you have an idea what could be causing the metal to stick in exactly those spots, let me know in the comments. But that still leaves one question. Why didn't this happen when I made my first perfect cesium ampoule years ago? My best guess is that the temperature was simply lower when I made the ampoule back then because I was using a much smaller torch. And that lower temperature prevented this effect from occurring. Even for the last ampoule I made myself for this video, I used a much hotter torch than I did back then, simply because the result looks better when I can properly melt the glass. So the higher temperature might actually be the cause of this problem. But I'm definitely not going to test that theory in today's video. After sealing the ampoule, you can see that, just like the previous ones, it's almost perfect. The metal looks absolutely beautiful. And honestly, at this point, I'm willing to accept that result. At least for this video. I've made a whole pile of stills, and for now, I'm done with glass blowing. But I promise I will figure this out in a future video. As I mentioned earlier, the small area where the cesium sticks can easily be removed by gently heating the upper part with a hot air gun until the metal evaporates. But after all these attempts, I ended up with 6 ampules instead of just 1. And I honestly don't know yet what I will do with them. I considered giving one away to a Patreon supporter or channel member, but international shipping for something like this is basically impossible. So for now, they will stay with me. Until I decide what to do with them, I needed a safe way to store them. So I printed a set of storage boxes using carbon fiber filled PETG. Even though I've never had problems with PLA, it is technically biodegradable and can become brittle after several years. PETG should remain stable much longer. At the moment though, these ampules are just sliding around loosely inside the box. So I added inserts printed from TPU air, which behaves almost like foam depending on the print settings. This way, the ampules are held securely in place and can be stored safely long term. And in my opinion, the cases also look pretty nice. In summary, I believe that during the first 2 distillations, there really was a problem with my vacuum system. You could clearly see oxidation on the cesium surface, and the thin film of metal inside the still also slowly oxidized. Once I added the turbomolecular pump, those problems disappeared completely. All the other possibilities I investigated after that turned out to be false leads. The cesium sticking to the glass wasn't caused by contamination, but by the surface properties of the glass itself. And in future videos, I want to investigate that further by producing ampules under different conditions. I had actually already uploaded this video to YouTube and even set a release date, but somehow it just didn't feel finished. I wanted to at least test my theory that the issue is related to how the ampules are made. So I went for a 7th attempt, this time trying to keep the glass temperature as low as possible while making the ampule. And finally, the result was an ampule where the cesium no longer sticks to the glass, at least in the upper part of the ampule. At the bottom, the issue still remains. But it seems like I'm on the right track, and for me, that's enough to make peace with it and bring this video to an end. Looking back, I might have been a bit obsessive about the cesium sticking to the glass, because everything after the 2nd attempt actually looks absolutely beautiful. Getting good video footage of the ampules is surprisingly difficult. The reflections on the glass make filming tricky, and even though photos have the same issue, I think they show the metal in a way video just can't. As the cesium cools, it forms beautiful dendritic crystals that sparkle in the light. There's a reason this is my favorite metal. And I really hope that anyone who sees this ampule in the periodic table will be just as fascinated by it as I am, and that it makes chemistry feel a little more real and tangible. I really hope you enjoyed today's video. Other than that, thank you a lot for watching.